Yes.
Nice. So let's begin. Um, Let me introduce myself. My name is Rogério. I'm from a city called Indaiatuba in Brazil, state of São Paulo. Um, I I worked at Serasa for 2 years. That's where I met Jake, and now I work as a senior engineering manager for a company called Unico that is responsible for uh, creating biometric engines for face recognition and using it as a digital identity. So that's what we do. I work overseeing two teams actually. The first thing is the one that uh, I, I actually I read said that it's the biometric engine, and the other team is the data platform engineer. So uh, that's what I do, and I really hope that you all appreciate the presentation. Actually, it's the first time that I do a presentation in English, so if some mistake, if I commit some mistake or something became a little messy, it's because I'm a little nervous because I'm it's the first time I present in English, but and actually sometimes I'll be translating from Portuguese to remember something. So that's it. It's a pleasure to be here with you all. And today we'll talk about storage and retrieval. And that's an interesting topic. And actually, it's based upon a book. Let me, uh, yeah, everything that I will say tonight is based upon this book. It's a great book, Designing Data Intensive Applications from Martin Kleppmann. It's a great book. It's about it, actually it covers a lot of subjects, but uh, there's a chapter that Martin talks about databases and storage engines. So let's begin making a distinction. Database almost always is an implementation of a storage engine. So that's the difference. Okay. Today I'll be talking about storage engines and not actually databases. Okay. This is the first thing uh, that I would like to know to do tonight. So okay. So the first thing I want to talk with you is what is a database? Actually, defining a database is pretty easy because database is something that you provide data and you want to recover data when you need it. Okay, that's it. Every, I think that's the best definition uh, I can make now. So, uh, are you seeing my presentation? Yeah. Uh,
Yes, we are seeing
okay.
it.
Okay. So since the database is something that you store something and retrieve when you need it, we can ask what is a good database? And the two pillars of a good database is basically two. The efficient, a good database needs to needs to provide you an efficient way to do key value lookups. So if you want a value of a key, a good database needs to do it efficiently. Okay. And the second thing we can say that a good database do is efficient range queries. So, for example, give me every key between A and B, for example, when A and B are natural numbers, for example. So every storage engine in the stock is judged against these two pillars, okay? Okay, so let's begin talking about what is an index. And this is a cornerstone when we are talking about storage engines, because an index is an additional structure derived from your data. It's a way you can find your data. Okay, it helps you to locate the value for a particular key more efficiently. If you don't have an index, you will literally need to look up for every value, and you don't want to do that. So an index is the most important thing in your database. But keeping additional structures around costs you something. That's and and that is exactly what we will talk about. Because well-chosen indexes speed up reads, but every index slows down your writes. And actually, junior developers, uh, it's pretty natural try to create a lot of index in and when they hope to make faster queries, but this is not true in most of cases, because when you add some index, you are actually slowing down your writes, because every structure you put upon your database will degrade, you will degenerate your database. So the first kind of index, and it's pretty straightforward when you think about it, is hash indexes. Hash indexes, okay? And hash indexes are hash tables, actually, but split across memory and disk. So suppose, let's look for the box at the right. So suppose you have some data, I don't know, user 42, the value is free, user 91, the value is pro, blah, 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 blah. Okay, so this is your data. But you want to be able to locate the value of a key in a time complexity O1. You want to do this in the most efficient way. And a hash table is the same idea as the in-memory hash table we learn when we are learning about data structures, okay? When you are in your computer science classes and you learn about hash tables, it's almost the same thing. But here, it's split in two, because the index itself stays in memory because it's faster, and the data goes to your disk. So the in-memory hash map holds every key mapped to a byte offset. And here we are talking about logs, but logs here is different from your system logs. Log for us and for this presentation it's something that you write after something. For example, the data file itself is a log. And it's append only. So writes are sequential, so they're fast. So every time you receive some data, you actually append at the end of the file. This is a log, okay? For now, for us, for this presentation, this is a log. And forget about system logs and Google Cloud logging, all those stuff. For us, log is just a file that stores values, okay? So the in-memory hash map holds every key mapped to a byte offset. So for example, the first thing we store here is user 42 free, for example. And after that, at the position 64, thinking in bytes, it's literally the byte offset, we have the user 91 pro. And after that, literally at the position 128, we have the user 7 value free, for example. So you store the byte offset of each key. So for example, user 42 offset byte, byte offset 192. User 91, you store the value of the byte offset 64. So every time you want to read a key, you just look up its offset in the hash map and seek to that offset on disk. That's where your data lives, and read the value. And the idea is pretty simple, okay? But let's talk about a real implementation of this idea. There's a database called RIAC, and it's a distributed key value store. And actually, the storage engine is called Bitcask, and it's literally the on-disk implementation of exactly the log structure hash table from the last two slides. It's a real implementation. It's pretty interesting. And one active data file receives all appends, and older files are closed and immutable. And a single in-memory index, the kdir, maps every key to file plus offset, so a read, it's one disk seek. You don't need to scan all the values because you have the indexes. And this is a great feat when the value for each key is updated frequently. For example, a counter of video game plays, for example. But there's a problem with hash indexes because it's pretty good when you talk about key value lookups. It's actually the time complexity, it's 01, it's 1 sig. But it's pretty bad when we talk about range queries because it's ON. You need to literally read every value from this range. And there's another problem. The hash table must fit in memory. Suppose you have just, I don't know, 8 gigabytes of RAM. If your hash map is bigger than that, you can't use this storage engine. And millions of keys are fine, but billions starts to be a problem. And on-disk hash maps means random I/O. That's because these live in memory, not disk. And range queries, like I said, are not efficient because hashing destroys ordering. For example, the last slide, oh, another one, the hash map, the hash map does not preserve order. Okay, so if you do a query like, oh, select, I don't know, blah 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 from table blah blah blah, where ID between 100 and 200, you need to look every value. So
Could I just ask, you said that the hash map doesn't preserve
of
order,
course.
but you said that the files are appended at the end, and then the hash is there, the place on the end. So shouldn't they all just stay in order because they're appended and they never move?
Okay, but appending a value at the end of a file does not mean order because suppose look at this example. The users are not in order, but suppose my query is asking the user 1 to user, I don't know, 10. Do you
Oh, okay. In
okay?
order. Okay, I see what you're saying.
Okay?
Hmm.
Okay, so hash maps, indexes are very interesting, but they are good only in one pillar that we are talking about, the key value lookups. But we need to solve the range queries problem. Okay. So the first idea uh, we can the first idea we came with is okay, we have a log it's a data file. And we can break into the log into segments. For example, we have a segment containing 4 values, a segment 2 containing more 4 values, and segment 3 that is actually not completely fulfilled. And you can always break the logs in fixed max size and start to appending at the end of those files. And actually, we can make operations between those segments. Actually, 2 operations, compaction and merging. For example, suppose you have the segment 1 and the segment 2. Both segments contains dog and cat, for example. When you compact something, you preserve only the most recent value. Okay, this is, for example, a way of compaction and merging, and you preserve the max size of the segment. Okay, and the segment 3 will continue until it gets the max size value, for example, and you can merge another segment, and you actually ends with a bunch of segments, but merged and compact, preserving only the last result. This is a basic idea we can use for the construction of something that I will talk about. Okay, so the first idea I want to talk with you is breaking the log into segments. And this is actually the cornerstone for something called SSTables. Okay, SSTables are a data file format with one extra rule. Key value parts are sorted by key. So into the segment, the keys are sorted. Okay, this is very important for us. But they still organize into segments, and you can still run the same operations on those segments. You can compact things and you can merge things. But because the segments are sorted, merging them is such a merge sort algorithm, like I hope you remember, because you can read side by side, copy the lost key, and repeat. Okay, this is a pretty simple algorithm. And now we have the segments but sorted. we can use it for something very interesting. And why do SS tables matter? Because now you no longer need every key in your memory. Suppose you have something like that. Suppose you have an SS table file, and this SS table file contains a lot of blocks. Okay, each block is a segment, like we saw in the earlier slides. And let's look, for example, inside one block. We have handbag, it's the key, and the value is 12, handcuffs, and the value is 40, and handful, and the value is 7, and handwork, and the value is 55. Okay? And suppose you want to know, and suppose in your query, you want to know where is the handiwork. Now, what is the idea? You will only store the index of the first key of each block. So the first key of the block 0 is handbag, okay? And the block 1 is, I don't know, handsome. And the block 2 is, I don't know, handy. And the block 3, blah, 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 and so on. What is the idea? I don't need anymore to store each key in my hash map. I only store the first key of each block. So suppose in your query, you want to get the value of the key handiwork. Well, you know handiwork, it's after handbag because the segments are sorted. And this is before handsome. So you need just to look at the block 0. And inside the block 0, you need to read each value. But actually, it's it's much faster than read all the values. And your hash map, it's really sparse now because you don't actually store each key value. Okay? Okay? The idea, it's clear?
It's clear for me. How do you
Nice.
calculate the ideal size of a block?
It depends on it depends on the implementation. We have a lot of implementations, and we can talk about one. For example, in LevelDB and RocksDB that actually implements this idea, the whole stack lives in one file. And there, I don't remember the size, but each implementation has a size. Your question is pretty good, but actually depends on each implementation. Okay. So inside the file, we have uh, something beyond the data. Okay, we have something called index. It's actually the sparse index from the 2 slides ago. We have a filter, for example. Oh, the key is not in the file. Stop. You don't need to search anything. For example, we will have something called footer. That is a fixed aside at the end of the file, findable without scanning, and points to the index. We have each implementation actually creates a kind of SS table. But the idea of an SS table is the one that I said to you. Okay? But why this is so important to us? That's because in 1996, there was a paper called the Log Structured Merge Tree, the LSM-Trees. And in 2006, we had another paper called Big Table, a distributed storage system for structured data. And the words we keep using the next slides, for example, the mem table and the SS tables are actually big tables coinage, okay? So the paper that coined the terms was the big table paper, okay? So why SS tables are important to us? Because they are used in the log structured merge tree that we will talk about now, okay? The whole algorithm, it's the following. Suppose you have a new key with a new value. You will add the new record to a balanced tree in memory. And if you don't remember what is a balanced tree, it's one that keeps itself evenly shaped as it grows, so no lookup ever gets stuck walking down on a long branch because they are balanced. And this balanced tree in memory, we call mem table. You can use anything you want. Okay, you can use the red black tree, you can use AVL, you can use, I don't know, skip list, I don't know. It's literally what you like. The second step is when the mem table, that is the balance tree in memory, grows past a threshold, you write it out to the disk as an SS table, and that file becomes the newest segment of the database. And this process is called flush. Okay? The step three is when you want to read some value from a key, you look in the mem table first, then in the most recent on disk segment, the SS tables. Then, if you don't find it, the next most recent, and so on. And for maintenance, the step four is from time to time, a background merge and compaction combines segments from the SS tables on disk and drops overwritten and deleted values, for example. And a delete is itself a write. It appends a tombstone, and the row only disappears once compaction runs. And again, every implementation has some some minor differences between them. And what is the whole idea? Okay, I have a new key and value. I write it into the mem table until it reaches the threshold. When it reaches the threshold, you have something called the flush, and the flush creates the key and value inside the SS table. And remember, the SS tables has fixed maximum size of blocks. And when you want to read, for example, the value of k, you will first read the mem table. If it's not there, the newest SS table. If it's not there, the next oldest, and so on. That's the whole idea about LSM-Trees. And as you can see, they are pretty fast on writing. But actually, it can take a little longer when you need to read, because suppose your value, it's, I don't know, in a very old SS table. You will need to read the mem table, the newest SS table, the next oldest, until reach your value, okay? And to prevent doing all this work and the key actually doesn't exist, it's why I uh, I said, for example, you can actually put a filter in your blocks. And first you ask the Bloom filter, and not in the file, stop. Okay, the index is never read. Okay,
Uh, can I ask
okay,
a quick question?
of course.
So I'm just thinking like a key value pair, right? So using this is a perfect slide to be on. So if you have, let's say your key is like a product ID,
Okay,
and then you have, a value, right?
okay,
Of let's just say 1, 2, 3, 4, 5, right?
okay.
Could you kind of explain how that would work? So it goes into the mem table and then it gets written into the SS table on disk as an immutable record, or is that correct? Or
Yeah, the SS tables are immutable, but you can always do the operations. You can create new SS tables using compaction and merging.
okay.
Okay,
Yep.
okay. Uh, but I don't think I get it. I get the example. Can you repeat,
Yeah,
please?
so let's say you have a product ID,
Okay,
and you're I don't know, company A, right? But then you get
okay,
merged into company B. So they want to merge their databases, right, and
okay,
consolidate. But they use different product ID values, right? So you would like have to merge that. Um, so if you wanted to change the values and from the SS tables, you would bring in company B's to company A's table
yeah.
and then merge and
Yeah,
sort.
yeah, yeah. Your example, it's pretty interesting because actually the best fit for your problem is not a database based on LSM trees. Actually, is the best fit is databases based on B-tree that I will talk a little
Oh,
later.
perfect.
But in your example, of course, we can use the LSM trees, but you will have a lot of problems reading all the files and merging the segments between the two databases. but the best fit is not an LSM tree. Okay,
Very
it's
good.
doable, but it's a little harder than B trees that I'll talk a little later.
Perfect.
Okay.
So it seems like LSM trees are really prejudiced towards um, an application where your information is mostly very new, where you're going to be accessing new information and not old
Yeah,
information.
it's a pretty good insight, and you're right. Okay. Okay. Um, since we talked about LSM trees, we saw that actually this storage engine, it's very good in key value lookups, but maybe it will take a little longer, but it's efficient. And it's very efficient in range queries because the segments are sorted by key. So if you search for, I don't know, key 1 to key 100, they are sorted. You will just read one after other. Okay, that's a pretty interesting storage engine. But now we'll talk about a pretty old technology. Actually, it's older than LSM-Trees. That is the B-Trees. And just a fun fact, B-Trees means nothing, okay? Literally, there's no meaning behind the B. It's just a name that the authors wanted to call them, okay? So in 1970, there's a paper by Rudolf Bayer that is called Organization and Maintenance of Large Ordered Indices. And in 1979, there's a paper called the Ubiquitous B-Tree. And those two papers are the foundation of a technology and a storage engine called the B-Tree. And let's talk about it now. For us now, we want to store our data in a specific file format, okay? And this file format it's composed by fixed size blocks, and these fixed size blocks traditionally for kbytes, it's called pages. And we start from the root page, that is this fixed size blocks, and you reach child pages through pointers. And the number of child references in one page, it's called the branching factor. In practice, hundreds. Okay. And actually, here I'm talking about the older ones because, for example, a Postgres use 8 kbytes and MySQL uses 16 kbytes. Okay, so the page size is chosen to match how the disk and the operational system move data. But okay, so how do we do updates, splits, and why it stays shallow? An interesting thing about B-trees, it's because most databases fit in a B-tree of just 3 or 4 levels deep, because a 4-level tree of 4 kbytes pages with branching factor 500 holds about 250 terabytes. Okay, this is the power of exponential. And updating the value of an existing key leaves the reference intact because, as I said, you have a root page. I will show you later, but you have a root page and you have pointers. So if you just change the value, it's okay. But adding new keys, it's more delicate, and it's not the subject of this presentation. But we can talk about it later. And the algorithm used in B-trees guarantees that tree of n keys stay balanced. So it's a balanced tree. And the height, literally the depth of the tree stays proportional to log of n. So the time complexity is log of n. So let's see an example. Suppose you want to look up the value of a key 250, and the root page contains references, that's actually the pointers, and values. For example, we know that 250, and this is an example, of course, it's between 200 and 300. Okay, let's see the reference, the pointer here. The pointer bring us to the next child page. Okay, and this child page contains again references and values. And we know that 250, it's between 250 and 270. And we look the reference. And at the leaf page, that's what it's called, we have actually the keys and the values. And now we reach the key 250 and the value that we want. That's how we can reach each value for some key. That's the whole idea of B-trees. And B-trees are very efficient in key value lookups, like I said, and efficient range queries, because here depends a lot in how the B-trees are implemented. But almost every implementation, the keys are stored in a sorted order, like we saw here. Okay, so range queries, it's pretty natural. But okay, which engine is better for us? Actually, as a rule of thumb, LSM-Trees faster, you have faster writes because everything is a sequential append, and the same data is rewritten later by compaction, and you have a higher write throughput. Okay, but B-Trees on the other side, we have faster reads because it's pretty straightforward. Okay, I want the value of some key, blah blah blah. You reach the leaf and you reach the value. Okay, and the cost of it's random writes because it happens in B-Trees, and every change it's written at least twice. Okay, let's see some real implementations of each storage engine. For example, the LS3 family, as you see, are almost every NoSQL database. Like the intuition that Jacob used here, it's right. Oh, when I want to have a lot of writes of, I don't know, events, and the most recent is actually what we need to use. Almost every time you have this situation, you will use a NoSQL database. So for example, the Google's big table is the ancestor, and Cassandra, HBase, and ScyllaDB all descend from it. Actually, ScyllaDB is the Cassandra written in C++. LevelDB is the reference implementation. RocksDB forked from it and now sits inside CockroachDB, blah, blah, blah. And here, on purpose, I didn't place here the Bitcask because Bitcask is not a LSM-3 based database because it's a log structure hash table. Okay, so that's not from the LSM-3 family. On the other side, the B-tree family is the most familiar databases we know because they are all relational. Okay, almost every database that is transactional uses some database based on B-tree implementation. So the classic relational world, every one of these uses a B-tree or a B+tree that we'll talk about later. And for example, SQLite, MySQL, PostgreSQL, Oracle database, MariaDB, DB2, that the people from Serasa knows a lot because of mainframe. So as we see, the two storage engines provide us a family of databases that actually is pretty different from nature because the way we store the things are different. Okay, so let's look for a real implementation of B-trees. The first one is called the clustered index, and actually this is the real implementation of the InnoDB, that is the storage engine behind MySQL. Okay, so what is a clustered index? A clustered index is specifically a B-tree index where the index structure itself holds the complete row. So the index is the table. For example, we have the internal nodes, and the leaves are actually the data. So for example, when you do something like that, create table, users, and you have an ID that is your primary key, you have a name and you have an age. Actually, the row, the whole row is stored on the leaves of the B tree. So the B tree is the table, okay? And the clustered index is the primary index, the primary key. And in the B tree leaves, instead of pointers to rows, you find the complete rows. So like I said, a clustered index is a B tree that is the table. The values you receive when you do a query is actually the B tree. And the physical order of rows on disk follows the primary key order. And this implementation is very efficient for primary key lookups and range scans, because of course you can have secondary indexes, but for primary indexes, it's pretty good and in lookups and range scans. So for example, here we have a difference, because if you study this subject, you will face a term called the B+tree. And what is the difference between B+tree and a B tree? A B+tree gives you some things that you don't have in a ordinary B tree. The first thing you receive, it's a linked list between the leaves. For example, in a plain B tree, the leaf pages are independent. Let's come back to here. For example, the leaf page, okay, they are independent because you have a lot of leaf pages for all references in this example for internal pages. So in a B+tree, every leaf is connected to the next one by a pointer, like a linked list. So why it matters? The engine can scan all the data linearly without climbing back up to the parent nodes. So that's what makes, for example, a query like where date between blah, 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 and blah, 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 so fast in this implementation. And another thing you receive when you use a B+tree instead of B tree, it's because in a B tree, any page, including the root, can hold a complete record. And a B+tree enforces a strict hierarchy instead. For example, upper pages only have keys, and they are used only to guide the search. But the data itself lives on the lower pages, the leaves, all the real data, okay? So you have more keys per page, you have higher branching factor and a shallower tree, okay? So it's pretty common when you study this subject, you will face B+trees instead of B trees, okay? But the difference is the ones that I told you. Okay, let's see another real implementation of B-trees, but it's a little trickier than the implementation of MySQL. That is the implementation of Postgres. The PostgreSQL doesn't cluster the table by default. The base table is stored as a heap table, okay? This term, it's pretty important for us, heap table, because for now, the difference, it's because the data don't live in the B tree itself, but it lives on the heap table. So the heap table stores complete rows in pages with no physical ordering. But the B tree indexes don't contain rows. They're leaves. And again, we are talking about B+trees, but their leaves hold a key plus the TID, that is the tuple identifier. For example, when you see a B-tree index in Postgres, you will find something like that on the leaf. Okay, the ID 7 and the TID 02, the ID 12 and the TID 11. What does it mean? It means that for the key 7, the value is stored at the page 0 in the heap table and the slot 2 on the heap table. So the row is 7 and 34. For example, in example, when we created, for example, a table called users containing ID, name, and age. So the value of the rows don't live at the B tree itself, but they live in a separate asset called the heap table. And the B tree itself only holds the pointers to this heap table. And these pointers are called the TID, the page number and the slot numbers, Okay, so when you want to read something, you find the key in the index, that is the B-tree, then use the TID to reach the page / slot in the heap. And this separation makes multiple indexes ship differently of the implementation of the InnoDB from MySQL, because a secondary index will be another B-tree on where the leaves contain the pointers to the primary key, and you need to scan again on the primary key to receive the value. So the Postgres gives you this chance to have multiple indexes, okay? And of course, this implementation, it's very efficient for key lookups, but it's less efficient for wide range scans because the heap isn't in key order, okay?
So you mind if I just ask a clarifying
Of
question just
course,
for myself?
of course.
So let's say in this example, I have, let's just say like all my my Claude chats, right? So you have a session ID. So you would want to use, let's say I use that, I want to look at, oh, you know what? Last 2 weeks ago I was doing all this stuff and I want to use a B+ tree, for example, to look at a range. So that range of time would be better versus if I knew I was going to be looking at a certain um, chat, but maybe throughout the course of like 2 months, right? Let's say I keep going back to it. I would want to use a B tree then because I'm looking up a specific key value pair versus a range of data, right?
When you say B-tree here, the
Or
B-tree on
yeah,
Postgres implementation only holds the keys and the TIDs, not the
okay,
values. The values are
gotcha.
inside the heap table. But um, as I can see in your example, if I got it, you want to make a search query to retrieve the data from, I don't know, some time ago. Okay. For
Yeah.
this case, I think that the implementation of MySQL will be better because, like I said, the data lives inside the leaves, and the leaves itself are linked because it's a B+3. On the Postgres, actually, we have a lot of fine tunings that we can do for a better performance. But in the first approximation, I think that the InnoDB will be faster than the PostgreSQL. I don't know if I answered you, but
No, I think that clarified my question. Thank you. Yeah. No,
okay.
that makes sense.
Okay. And what the clustered and heap choice costs you. For example, in InnoDB, the secondary index leaves hold the primary key value and not a physical pointer. So every secondary lookup is two traversals. The secondary B-tree, you get the primary key, and now you need to look to the clustered index. That is actually another B-tree. And in Postgres, the index leaves hold the TID, and that it's actually a physical location at the page and slot inside the heap table. And we have something very interesting in Postgres that is something called a hot update, because when you move the tuple, literally, if you move the tuple, and every index on the table itself has to be updated, because when you do some change in your B-tree, actually you are changing the heap table. So there's something called the hot update, and it's a heap only tuple that avoids that. It's a mechanism for Postgres. And we have a lot of mechanisms pretty advanced in Postgres. It's a great database, okay, guys? And you have something called, for example, the fill factor. You have process that runs on background called vacuum that is constantly cleaning up the old row versions left behind in order to make faster queries, for example, in range queries. And you don't need to look to older versions or something like that. And as a practical rule, you can always watch your hop update ratio, for example, using the this is statistics. Of course, I'm overseeing the whole subject. Postgres it's itself a whole world about databases, and you have a lot of tools that can help you to have a good performance. But okay, All we talked about today are OLTP databases, okay? Online transaction processing databases, that is the name. Because what we have seen so far are the two main schools of thought behind transactional databases, the LSM-Trees and the B+Trees. And like you saw, almost every database we know can be placed on one of those two families, okay? But transactional systems typically serve end users, which usually means a high volume of requests, each touching a small number of rows. That is the definition of a transactional world. And the pattern here is you need almost always fetch a few records by key, insert or update a few records thousands of times per second. That's the major problem that we face when we are talking about transactional engines and transactional applications. Okay, but what's the problem? Not the problem, but it's very interesting for us to know. Both engines store data row by row. Even the LSM trees that we store the value that is actually the row itself linked to a key, and the B+Trees implementation, because we always store the row. And so that's why we call those databases built on B+Trees and LSM-Trees stores data row oriented, okay? And in a B-tree, all the data for a row sits in the leaves. And on LSM-Trees, we have the same thing because the content is linked to the key, like I said. But what is the problem? Suppose you need to read 3 columns, for example. If your query needs 3 columns, the engine loads every column of every row because they're glued together on the page. And the second problem, it's because we have an inefficient INO, because a huge volume of pages pulled from the disk. Most of it I will not need because I only need 3 columns, for example, in our example. And we have problems when we need to do queries that needs the whole data, for example, for a column. Suppose a pretty easy example, select region and you use some aggregation function like sum, and you are querying those data from a table called sales, and you need to group by region, okay? When you need to do something like that, row-oriented databases is not the perfect fit, okay? That's the beginning of another subject that we'll not talk today. That is the column-oriented storage. That is the whole world that data engineers face every day because the need is different, because the needs of a data engineer almost always is related to whole columns. But from a transactional perspective, you need a very few rows for a very few keys. So the purpose is different between these two approaches. But what I want to make clear today is that we have 2 main schools of thought about databases. We have 2 schools of thought about how we store data. That is the LSM trees and the B trees. But both of them are based upon rows. And when you need to look a huge amount of data related to some specific column, it's where you need to change your approach for a different database, a different storage engine that is called the column-oriented storage. That I hope I can tell you some other day. Guys, I tried at my best to give the whole presentation in 45 minutes, but I think I
Excellent. That was excellent. That was perfect. And I definitely learned some things today.
Nice, man. Do anyone have some question? I'll be pretty happy to try to answer that.
maybe on like the cybersecurity side of things, just a unique aspect of, kind of possibly off topic from your presentation, but what about like, so you salt the hash table is what I've been told. Is that correct? Making encoding the data so that, you're not just printing, plain text. Um,
Yeah.
yeah.
There's a whole world about how you encrypt your data. And there's another problem related to your question. That's, of course, in our examples here in our presentation, I've always used plain text. Of course, there's a whole of methods of encryption and how do you protect your data. And actually, as a fun fact, there's a whole res research line that is called homomorphic encryption. And this is pretty interesting because homomorphic encryption, it's based on idea that we can do algebra using encrypted data. So the basic idea is, okay, I have only encrypted data. How can I do operations, algebraic operations using those data? And but I will never see the real data. So those kind of ideas, it's pretty interesting, and they are always related to the way we store things. And of course, we can create a bunch of levels of security and on how we store data and something like that. It's a very interesting from a cyber security standpoint.
Yeah, that sounds really fascinating. You said homomorphic encryption?
Yeah, it's very interesting. Actually, there's a lib from Microsoft that is the one of the only ones real implementations of it. But actually, it's very computing expensive, so it's not good for a good production environment. But it's a pretty interesting uh, idea related to how we store data and how we can actually transform the data, but never seeing the data. It's very interesting.
Yeah, yeah, absolutely.
That is crazy. So, the idea behind homomorphic
Jacob, I think
encryption.
it's. Oh yeah,
Are you hearing me now?
yeah.
Sorry, I had my microphone pointed away from my mouth. So
No
that's pretty
problem.
crazy. The idea of a homomorphic encryption and one of these libraries that would allow you to manipulate this data is that you could encrypt your data with your private key, and maybe you encrypt two pieces of data, and then maybe you want to sum them together, and you're actually able to do some sort of arithmetic or manipulation to
Yeah,
these two pieces of data without ever seeing the real
yeah.
data, and then use
That's
the
the idea.
private key to unencrypt them again.
Yeah, that's the idea.
Hmm. It's crazy. I've never heard of something like that happening. Wow.
Yeah, we are living crazy times, man.
But it's very computationally expensive.
Very, very.
Yeah.
It's not feasible on real production environments.
What about, I know there's like because like, what is it, RSI, RSA, and ED encryption or SHA? Like, I know that there's a move now to go like, what is it? They call it quantum encryption now, right? So is that going to increase our compute demands just to stay encrypting in general, even when running these database queries?
You are asking if those kinds of
That might,
encryption.
yeah,
Sorry,
I don't
sorry.
know how that affects. I guess my question is like, does any additional encryptions really affect your work in general with databases right now?
No,
Um,
no, I don't think the way you encrypt your data changes, I don't know, performance metrics. I don't think that it happens. But you touched a very interesting point that is a whole field of study that is related to which one of our encryption methods will survive after, for example, a quantum revolution or something like that. For example, the RSA encryption that is based on prime numbers will be the first one affected from a quantum perspective, because we have a lot of algorithms. For example, the Shor algorithm that is responsible for factoring a number in prime numbers that can be used, for example, to break on RSI encryption. And we have elliptical curves that will not survive again for a quantum revolution. But man, cryptography is a very interesting subject, but and it's very correlated to what we're talking about. But I don't think the way we encrypt our data affects the database performance itself. I don't think that.
Okay. I have another question too. If nobody else, I'll let somebody else go ahead first, but
No, go ahead.
okay. So how have you been implementing AI with your work, and have you seen noticeable gains in, whether it's the amount of work you can do or efficiencies or just like your life getting a little bit better? Um, so
Yeah.
just curious.
No, it's a good question. When we talk about AI in our company, uh, actually, let me tell you a story. I think a few weeks ago, I went to an event from Google uh, for the leadership of some companies, and we talked about the AI inside our companies. And Google provides us the 4 levels of AI uh, inside a company. The first level, it's when you use AI just for personal productivity. So you use AI as a harness for coding, I don't know, something like that. The second level, it's when you actually create agents that affect your toil. So you minimize toil from your team. You start to create agentic solutions for your problems, blah, blah, blah. The third level is when actually we start to use your agents to affect the business itself. So the clients and something like that, not just for internal purposes. And the fourth level, it's when you actually create a customized LLM that uh, that your agents are based upon. And the last level, it's what they call the hyper customization. Okay, so answering for my perspective, my company, it's between the level 1 and 2. We use AI for personal productivity, and we are starting to use agents to solve our problems and reduce our toil. But I don't see yet we using AI, for example, uh, talk with clients or make decisions or something like that. And of course, we are pretty far from the fourth level, because actually I don't think that there's a lot of companies on the last level, because actually it needs to fine tune an LLM to uh, encapsulate the data from your company, your organization, your code, so your agents, of course, will act a lot better because they are based upon an LLM fine-tuned for your necessities. So that's why I think my company leaves.
Yeah. Yeah, that's interesting stuff because I know like when LLMs were a lot worse, there was this kind of movement we started seeing because fine-tuning some models was relatively like it's relatively cheap. But you need to have a lot of, let's say, proprietary data, right? So it's more advantageous if you're, say, some big research company or some just or multinational companies especially,
Yeah.
right? Um, but now we're starting to see, for a different reason, we're starting to see them more fine tuning to reduce cost of saying, hey, let's self-host our own model because we're spending, tens of millions of dollars a month in just API, in frontier model tokens, right? So you're starting to see kind of some of that come into play, and what's the right move? I don't know. Um, but from the database side too, I'd be curious, like, do people ask you all the time to like create reports? Is that part of your job where you have to be like, hey, can you just tell me, like, I want this information, and can you just find it for me? Just
uh,
generic, like, okay.
you were asking me if the people from the company ask me for reports about databases.
Yeah, I was just curious, like, with your role, is it more in like, because I don't know, sometimes somebody might ask me like, oh, like, or somebody may ask me like, hey, like, I'm working on our Workday, they have Workday, HR database access,
Okay.
right? And they're like, well, how can I use AI to do this? I don't really know what I'm looking for. And they can't describe, like, maybe they're not like a really good tables person, right? They just, that's not their strong suit. But um, so I'm like, okay, let me help you research how to create a nice
Yeah.
report and get what you're looking for from this,
Yeah.
you know.
Actually, that's not specifically my team. There's a team
Sure.
that's called data analysts, and they are
So it's more on them
pretty
for you.
and
Yeah.
and they are actually teaching the whole company how to use the LLMs and how to use the MCP servers from, I don't know, BigQuery, for example. That's where the data lives, and how they can use the LLMs to provide, for example, those kind of reports or dashboards. And a very interesting topic about that, it's because the Google Cloud, it's pretty good about data, and they actually have a product called the Knowledge Catalog, and that is actually a catalog for data. And if you have a good catalog and you have data with good metadata about, I don't know, column descriptions, table descriptions, when you use the MCP server from BigQuery, for example, in your LLM, man, actually it gets it's pretty good. And you get a lot of good results, and you can use those data, for example, using another service from Google, for example, Looker, and you can use Looker, for example, to create dashboards or reports like that, like you're asking me. Uh, Actually, I worked at Carrefour. Carrefour is a big retail company in Brazil, and when I worked there, there wasn't LLMs yet, but I remember that those kind of requests, that there was again a team called the data analysts, but all they used to do was actually do what the LLMs do for us today. They they read all the catalog, they use it to read the description of the tables, and they used all those analytical data to create dashboard or create data marts that the business areas could rely on decisions.
That's, yeah, very interesting stuff going on right now, I think.
Praise time.
Hey, so circling back to databases, I had a question specifically about relational databases. I use relational databases at work and on all of my personal projects, and I've kind of been defaulting to Postgres. And I know that like SQLite is the most used database in the world. And I I can't remember if you actually mentioned some of the factors that would go into a decision like this, but when you're developing a web app, um, what factors would you consider on what relational database to implement into this web app? Maybe factors like the if you have a very large number of primary keys or you have very large files that are stored inside of those primary keys or large pieces of data. What factors would affect that decision?
I think there's a thing before all of this. It's the actual need of a transactional database. It's pretty common when we talk about web applications that we need NoSQL databases. But suppose you you already decided for yourself that you would use relational database. Okay, the first thing we have to think about is, okay, how much data will we store? Say, I think this is the first funnel that we will face. Okay, I think that we will face, I don't know, billions of users and billions of requests every second. Okay, this decision actually moves you toward more mature implementations. For example, Postgres or I don't know, Oracle, something like that. But suppose you have, I don't know, I don't have so much data, and okay, so this gives you the chance to use uh, more compact versions because every every choice you made about about what implementation you will use, it costs you a lot because, for example, maintaining a Postgres server, a Postgres database, it's pretty hard because there's a lot of configuration, a lot of fine tunings you can do, and most of cases you actually don't use the whole suite of tools that the Postgres provides you. So, for example, in a case that you have a simple web application, maybe a MySQL implementation, it's good for you. But oh no, I need to handle a lot of indexes. Like we said, Postgres is pretty. It's so better than InnoDB. That is the implementation for MySQL for this case because you have multiple indexes. But okay, no. Beyond that, I need to have availability across multiple regions. So we are not talking about Postgres anymore. Maybe you need a spanner from Google, for example, that you have multiple regions availability. So I would start thinking the first question, okay, how much data I will face every second, and okay, the next level is okay, how many indexes we have in our data modeling and things like that. There's no there's no a correct answer. It's always a trade-off. Okay, and we need as engineers know a little about every implementation. So if you get all this information about the major implementations, you will always know which one is better for your needs.
Thanks. That's a very comprehensive answer. I actually want to go back to the very first thing you said was that many web applications might not need a relational database. Um, and why is that?
There's a question.
Yeah.
Oh, it's not correct to say that they will not need a transactional database. Of course, they always can have a transactional database, but usually web applications deals with events, and events are pretty well handled by NoSQL database because, for example, MongoDB, it's a great database that only Mongo itself can handle your whole web application because it is pretty good for events and it's pretty good, for example, for I don't know, kind of things like product database, product catalog, or users catalog, users database. You can always use NoSQL database for web applications. I'm a pretty fan of MongoDB, and MongoDB can almost replace all of the other flavors of databases. MongoDB is a pretty powerful database. We have, for example, I don't know, the big table itself. It's a great database, but of course it's expensive because it's inside GCP. But you have open source options like HBase. I don't know, some other options are using. Actually, the Mongo itself has a free version of it. So it's pretty common you have scenarios when you don't need more than a Mongo, for example. And actually in AWS is the document DB, for example. And it's like I said, it's always a trade-off between your needs and what you want to do.
So it sounds like you really need to kind of best guess and predict up front to make the best decision.
Yeah, you can always, of course, rely on more mature decisions. You can, okay, you it's good to know a little about the major implementations of each storage engine. For example, okay, I know uh, pretty well about Mongo. I know it's an example. Okay, suppose I am an engineer that I know about Mongo. I know about Cassandra. I know about Postgres. I know about MySQL. I know about Oracle. If you know those five, for example, you'll be in a so much better place to decide which one is the best fit for your needs. Because and actually, if you do that, you'll be ahead of the most of engineers in the world, because almost ever they even don't know what database to use, because oh, it's the same thing. Okay, let's use Postgres for everything. But Postgres, it's like a bazooka for some cases. Postgres has a lot of tools, tooling for fine tuning things and control the flow and something like that. And I don't have a conclusive answer, because, like I said, it's always a trade-off. Trade-off.
Yeah. For me, at least, when I first started, probably my first like 20 projects, I think it was straight to Postgres because I'm like,
Yeah,
well,
yeah, it's
I
the
don't
most
know anything
famous. Okay,
else.
let's go. Let's go with it.
And I probably still to this day only know like 15% of how to use it. I never optimized myself to be the best database guy, right? I took the time to upskill in different areas,
Yeah,
but
yeah, and that's not a problem at all. And but it's very good for us to challenge ourselves to know more about other implementations. Like I said, I don't know, MySQL, MariaDB, I don't know, stuff like that. Even the RIAC, the Bitcask implementation that uses hash tables, for example, maybe we have a use case for that in some application that we are dealing with.
So we use AWS at work, and I use AWS with some of my personal projects. And there are various cloud providers that provide managed database services, like the MongoDB service for AWS is DocumentDB.
Yeah.
And what are the trade-offs if you're an engineer thinking about running a database on your own EC2 versus having a managed database?
The price.
yeah.
That's the difference. Everything that is managed by AWS or by GCP, it's always ex more expensive than you in comparison to handle and maintain your own instance of database. The price is the answer. If you have money, you can use the managed database.
Do you think it's advantageous to use the managed database
Yeah,
usually?
I love managed things, man, because it minimizes a lot of toil that we have, and that's why the cloud providers are rich, because they provide us a way to not depend, for example, in a team of 20 DBAs inside our company, for example.
Awesome. Hey, Kevin, did you have anything to add? Any pressing questions, Mr. Kulat?
Not questions. I look forward to the column database talk. This was a good primer for what's to come, if that's the intent.
Nice.
And very well
Man, I'm
presented, might I add.
Yes.
I'm glad you said that because that's the exact signal we need to know that we need to come back and do another one of these in a few months and talk about column-based DBs.
Nice.
Well, good. I think this is a pretty good stopping point then.
Yeah.
Yeah, I'll go ahead and end the recording now and
Thank you very
Uh,
much